A spacecraft launched when Disco was still on the radio just detected something at the edge of our solar system that scientists never expected to find, and it has forced researchers to rethink what actually happens, where the sun's influence finally runs out. This is the story of Voyager 2, the discovery it made in the emptiest region humans have ever explored, and why that single finding continues to shake up decades of assumptions about the true boundary of our solar system, and what it might mean for everything we thought we understood about the space beyond it. To understand why this discovery mattered so much, it helps to picture exactly where Voyager 2 is. Launched in 1977, the spacecraft spent its first 12 years flying past Jupiter, Saturn, Uranus, and Neptune, becoming the only probe in history to visit all 4 of the outer planets up close. After that historic tour, it kept flying outward, year after year, decade after decade, until it finally crossed into a region no spacecraft had ever charted before. In November 2018, Voyager 2 pushed through the Heliopause, on the invisible boundary where the constant outward rush of particles from our sun finally gives way to the cold, dense material drifting between the stars. Crossing that boundary made Voyager 2 only the second human-made object ever to leave the protective bubble the sun creates around our entire solar system, following its twin, Voyager 1, which had made the same crossing 6 years earlier at a different point along the boundary. Scientists had spent decades building models to predict exactly what this transition should look like, based on theory and on the limited data Voyager 1 had already sent back. When Voyager 2's instruments started reporting from the other side, however, several of those predictions turned out to be wrong in ways nobody had anticipated. The most startling discovery involved the density of the plasma surrounding the spacecraft. Inside the heliosphere, the bubble carved out by our sun, plasma is extremely hot but very sparse, thinned out by billions of miles of expansion as the solar wind pushes outward in every direction. Once Voyager 2 crossed into interstellar space, its plasma science instrument detected something researchers were not fully prepared for. The plasma on the other side of the boundary was measurably denser than the plasma inside the bubble, even though it was also far colder. That finding matched what Voyager 1 had already reported years earlier, and having 2 independent measurements confirming the same surprising pattern turned a curious anomaly into a confirmed feature of the boundary itself. What made the density readings even stranger was a detail scientists picked up in the approach to the crossing itself. Just before actually passing through the heliopause, Voyager 2's instruments recorded a distinct increase in plasma density, as if the material were being squeezed or compressed right at the edge of the bubble. The same kind of compression showed up on the interstellar side as well, suggesting that something was piling up pressure on both faces of this boundary at once. Researchers still do not fully agree on what causes that compression, though competing theories point to interstellar magnetic field lines draping over the heliosphere or interstellar material, slowing down as it runs into the edge of the sun's domain, creating something like a traffic jam of charged particles. Perhaps even more unexpected was what Voyager 2's magnetic field instrument found once the spacecraft had fully crossed over. Researchers had generally assumed that the magnetic field beyond the heliopause would point in a noticeably different direction than the magnetic field inside the bubble, since the 2 regions are shaped by completely different physical processes. Instead, Voyager 2 confirmed a result that had first surprised scientists when Voyager 1 reported it years earlier. The magnetic field just outside the heliopause runs roughly parallel to the magnetic field inside it. That alignment was not something existing models had predicted, and it hinted that the relationship between our solar system's magnetic environment and the wider galaxy's magnetic field is far more complicated than researchers had assumed. Voyager 2 also revealed that the boundary itself behaves less like a solid wall and more like a permeable membrane. One of the spacecraft's particle detectors picked up a steady trickle of charged particles from inside the heliosphere, leaking out into interstellar space, slipping through the boundary in a spot researchers now believe is more porous than the location where Voyager 1 crossed years earlier. Because Voyager 2 crossed the heliopause closer to the side, or flank, of the heliosphere's bubble shape, rather than near the leading edge where Voyager 1 exited, the region turned out to allow far more particle exchange between the 2 environments. Scientists compared the effect to a ship's hull that, while mostly intact, still lets water seep through in certain weak spots along its surface, and they noted that the amount of leakage detected was greater than most existing models of the heliosphere had anticipated for a region this far from the boundary's most exposed point. There was also a puzzling detail about exactly how and where both spacecraft made their crossings. Researchers expected the heliosphere to expand and contract somewhat depending on how active the sun happened to be at the time, since a more energetic sun should push the boundary further outward. Voyager 1 crossed the heliopause while the sun was near a peak in activity, sending out frequent bursts of solar material, while Voyager 2 crossed years later during a much quieter period on the sun. Based on existing models, the boundary should have contracted inward during that quieter stretch. Yet both spacecraft ended up crossing at almost exactly the same distance from the Sun, only a few astronomical units apart. That inconsistency left researchers acknowledging that models taken at face value would have predicted a noticeable difference, one that simply never showed up in the data. The cosmic ray readings told their own strange story as well. As Voyager 2 approached the heliopause, its instruments recorded a steady rise in the flux of galactic cosmic rays arriving from outside the solar system, paired with an equally steady drop in the number of lower energy particles streaming outward from the Sun. That crossover pattern matched almost exactly what Voyager 1 had recorded years earlier at a completely different point along the boundary, which struck scientists as an unusually tidy coincidence given how different the two locations turned out to be in other respects. The team studying the data noted that this particular similarity was almost more surprising than the differences, since so many other readings between the two crossings had turned out to diverge in unexpected ways. Even the timing and geometry of Voyager 2's crossing hinted at deeper mysteries scientists are still trying to untangle. Because Voyager 2's plasma instrument was still fully functional at the time of its crossing, unlike a similar instrument on Voyager 1, which had stopped working decades earlier, researchers were able to directly measure the speed, temperature, and density of the material outside the heliosphere in a way that had never been possible before. Those direct readings confirmed the spacecraft had truly entered the interstellar medium rather than some ambiguous transitional zone, but they also revealed that the plasma just beyond the boundary was not yet the calm, undisturbed interstellar material scientists had expected to find. Instead, both Voyager probes appeared to still be moving through a kind of disturbed transitional pocket, shaped and perturbed by its close proximity to the heliosphere itself, meaning that truly pristine interstellar space might still lie some distance further out. This idea that the boundary region is more complicated than a single clean line has reshaped how mission scientists think about future exploration beyond the solar system. Researchers have pointed to complementary missions like the Interstellar Boundary Explorer, a spacecraft that studies the heliosphere from a much closer vantage point near Earth, as tools that help place Voyager's up-close, single-point measurements into a broader context. Combining data gathered right at the boundary with the wider mapping techniques used by missions closer to home has allowed scientists to build far more detailed models of the heliosphere's true shape than either approach could achieve entirely on its own. Even the process of crossing the boundary itself defied expectations. Many scientists had assumed the transition from the solar wind's territory into true interstellar space would be a gradual affair, stretched out over days or even weeks as the spacecraft passed through a thick, fuzzy transitional zone. Instead, both Voyager probes crossed the heliopause in under a single day, snapping from one environment to the other far more sharply than the models had anticipated. Just before the abrupt transition, however, Voyager 2 did detect a distinct boundary layer roughly 1.5 astronomical units wide, where the plasma slowed down, heated up, and became roughly twice as dense as the typical plasma found closer to the Sun, a narrow transitional pocket, squeezed just inside the true edge. Taken together, these findings came from 5 separate scientific instruments aboard Voyager 2, each one detecting a different piece of the same unexpected picture, and the results were significant enough that researchers published 5 separate papers describing them in the journal Nature Astronomy. Having that much independent cross-check data allowed scientists to feel confident that what they were seeing was not some instrument glitch or measurement error, but a genuine, previously unknown feature of the region where our solar system meets the rest of the galaxy. Edward Stone, who served as the Voyager mission's project scientist for decades, said at the time that discoveries like these confirmed there were still more surprises waiting for the twin spacecraft as they pushed further into unexplored territory. Researchers involved in the analysis have described the process almost like piecing together a puzzle with pieces arriving one radio signal at a time, each new transmission forcing small revisions to a picture that seemed settled only months before. What makes all of this even more remarkable is that Voyager 2 was never actually designed to make these measurements at all. The spacecraft's original mission, planned back in the 1970s, was built around a 5-year tour of the outer planets, with nobody on the engineering team seriously expecting the probe to still be functioning, let alone gathering groundbreaking data nearly half a century after launch. Every instrument still returning usable readings today is operating years, and in some cases decades, past its intended lifespan, squeezed along by careful power. Management as the spacecraft's plutonium generator slowly loses strength with each passing year. Mission engineers have had to shut down several instruments permanently over the years, simply to keep enough power flowing to the ones still capable of returning in genuinely new science from this unexplored region. Because Voyager 2 and Voyager 1 crossed the heliopause at different locations along the boundary, their combined data has given researchers something no single spacecraft could ever provide on its own: a rough three-dimensional sense of the heliosphere's actual shape. Rather than a smooth, symmetrical sphere, as some earlier models suggested, the evidence increasingly points toward a lopsided, almost comet-like structure, compressed on one side and possibly stretched out into a long tail on the other, shoved into that shape by the solar system's motion through the surrounding interstellar medium. Confirming details like these would have been essentially impossible without two independent spacecraft crossing the boundary at different points, separated by both years and by geography, and scientists have openly acknowledged that a third or fourth crossing point, if it were ever possible, would sharpen that picture considerably further. None of these findings answer every question researchers have about the true edge of the solar system, and in many ways the data has raised as many new questions as it has resolved. Scientists still do not fully understand what causes the compression seen on both sides of the boundary, why the magnetic fields align the way they do, or how porous the heliopause truly is at other points around its surface that neither Voyager has ever visited. Each of those open questions has become the subject of ongoing research, with scientists continuing to comb through years of archived Voyager data, hoping to extract new insights that earlier analyses may have missed entirely. And some researchers believe entirely new discoveries are still hiding within readings that have already been sitting in storage for years. Today, Voyager 2 continues drifting even deeper into interstellar space, still sending back data from a region of the cosmos that remains almost entirely unexplored by any other instrument humanity has ever built. Every new reading it manages to transmit adds another small piece to an increasingly strange picture of the true edge of our solar system, one that has already overturned assumptions scientists held for decades before the spacecraft actually arrived there. Right. Early 50 years after its launch, this small aging machine keeps proving that even our most confident predictions about the universe can be upended, one faint signal at a time, from a place no human being has ever seen with their own eyes, and one that continues to reveal new secrets. With every passing year, it somehow manages to survive.